Chapter 15, Lesson 4. This should be a short lesson in contrast to the previous one. And here we'll talk about something called the reaction quotient. Now, we had talked when we did the previous examples about there being two different states. There being initial conditions, and then there'll be equilibrium conditions. So we'll give you two reactions, the initial reactions and then the equilibrium reactions. And as we go toward equilibrium, those initial reactions will change. And we had the icebox for this. And here we're going to use the reaction quotient technically to show us whether we are at equilibrium, if we have reached equilibrium yet, and if not, which direction the system will go to reach equilibrium. So the quotient, in a way, looks at the change portion of this process. So it tells you if the system is at equilibrium, and the way we'll calculate it is pretty simple. We'll substitute the initial concentrations into the equilibrium expression, and remember the equilibrium expression is K, and technically K is at equilibrium already, so Q is defined the exactly same way, except before we get to equilibrium. And then so that reiterates that here Q gives the same exact thing, except for something that's not yet at equilibrium, and it's used to check if we are at equilibrium. So here's the general rundown. If Q is equal to K, then we have reached equilibrium, because remember Q is defined in exactly the same way. So if the two are equal, we are at equilibrium, our system has reached equilibrium. If, on the other hand, Q is greater than K, then what we have is we have much more products than we have reactants, and the equilibrium will have to shift to the left to replenish some of the reactants. And the way to think about this, remember both Q and K are defined as products divided by reactants. So if Q is greater than K, then Q is too big, which means we'll have to reduce this, reduce the top, and increase the bottom. And because the top are products, then we'll lose some products and gain some reactants. So that's if Q is greater than K. And then the last possibility, if Q is less than K, then the opposite is true. We have too many reactants, and the system will have to shift to the right to replenish some of the products. If you think about this logically again, Q, again remember, is products over reactants, so Q is now too low, which means we'll have to increase the top of this ratio and decrease the bottom, and as we do that, we equal out. A quick way to know this, or a quick little trick, whether this helps you or not, is think of listing this always as first K and then Q. Sometimes this helps. If you instead of listing Q and then K, if you go down the alphabet, K, we see K, the letter K, before we see the letter Q. And if you do it this way, and then you say, well, Q is less than K, then this less than sign always shows you in which direction the equilibrium will shift. It'll always go to the right. And likewise, in the previous example, if you take a look, we'll fire back. If you list K first and then Q, Q is greater than K, well, the system needs to shift to the left. This is a little shortcut that it's better to understand why, but you can also use this little shortcut to do the problem. So why don't we try a problem, and we'll wrap it up just with this problem. So here we have at 448 degrees Celsius, we have an equilibrium constant for the reaction given to us as 51. In fact, this is the same one we've been working with now. And then we're asking predict how the reaction will proceed, in which direction, to reach equilibrium, if these are our starting concentrations. We have 0.01 Hi, 0050 H2, and 0.015 I2. So let's go ahead and plug these values into Q. Q is defined in exactly the same way as K. So remember, in this case, Q would be Hi squared divided by H2 times I2. Let's go ahead and plug the values in. Hi is 0.010. This number gets squared. H2 is 0.0050. multiplied by 0.015. Go ahead and plug these numbers into your calculator and see what you get. Hopefully you got a value like this, 1.33 for Q. Now if we take a look and compare that against K, we see that Q is smaller than K. So since Q is smaller than K, in order to get to K, Q must increase. So Q is too low. So in order to increase, we'll have to increase the numerator and we'll have to decrease the denominator, which means we'll form more product. So the answer is it will shift toward products. And that's our answer. If you want to do the shortcut way, remember we said list K and then Q, and then we say that Q is smaller than K, and we see that the system must shift to the right. And on the right side we have products. And that's a simple equilibrium quotient problem. And this will conclude lesson 4 of chapter 15.